Okay, so how was your holiday? Mine was quite terrible. Anyway, but let's start our lecture 10. Okay, so today we have two topics. One is spacer formation, and another one is source drain one. But source drain epitaxial growth will be covered through multiple lectures. So first, let's go to our spacer. This is a top view of this one. This is a top view of our current structure up to now. So we have made the dummy gate. So although not shown here, everybody understand there are certain fins running in these horizontal directions. They are not seen because they are covered by other materials. So we assume that there are fins, but they are not shown. And this yellow one, so of course the color really depends on situation, but this is corresponding to dummy gate. So here we have a dummy gate and another dummy gate, and pitch between these neighboring dummy gates are given as 54 nanometer depending on the case. So CPP, this is the CPP, and CPP was, yes, in this AS87 PDK we assume 54 nanometer, but in reality, so our 7 nano technology showed a little bit longer length, but it's just okay. And nowadays the CPP of currently available technology is around 40 something nanometer. So it was 7 and we are now talking about 3, 2. So if they are really scaled according to their numbers, then we must have something like 20 something or 30. But as you can see here, CPP is not scaled any further. So this is one observation. And quite recently, so there was a report on the ultimate limit of a CPP value. Okay, now we are around 45, yes. And what will be the ultimate value of a CPP downscale? And according to Huawei engineers, they have found that this number would be 38 nanometer. So 40 something and 38, where we have only in terms of length scale, we have only one generation ahead, away from the ultimate limit of our SCPP scaling. So that will be the ultimate number. So when we think about this CPP number, CPP is actually can be decomposed into two numbers, and one number is of course this 20 nanometer corresponding to later gate length. This is currently just amorphous silicon or polysilicon, but later it will be just filled with other materials. So this is 20, and of course 54 is a sum of 20 plus 34. This green line or green layer is corresponding to that layer, and that is our today's topic. Here we have space between gates. So this is 34 nanometer long, and here we must introduce our source and drain, because everybody understand this is a gate. So we have to place our whether which one is a source or which one is a drain, it really depends on your operation. but source and drain, or drain and source should be placed within this 34 nanometer. So I remember that actually I introduced the reason why we have to introduce spacer here. If we really fill our 34 nanometer entirely with this source material and drain material, then that will be quite good in terms of resistance, but there is a strong capacitive coupling between source and gate and drain and gate. It's not acceptable. So we must separate these contacts one by one. So that's the reason why we need to introduce certain structure, separate this possible source and possible gate. We must introduce something here, and also quite equivalently we must introduce something here. And also, although right now we are now showing the inverter structure, so actually here we have a source and drain, and this gate is not actually used. If you remember correctly, even our fin itself was cutted in that way. So this is the under shape of our underlying fin, although that is much thinner than my drawing. But point is, now it was cutted. But instead of this simplest inverter structure, think about more general structures like we have still more dummy gates and also dummy gates. In this case, we have to also introduce another transistor here, there. So we have a long chain of transistors. So in this case, well, this one is the real transistor. Also, it requires separation. So we will have another spacer from this point and from this point. The reason why I'm talking about this one is still we have a 34 nanometer, but that is not entirely reserved for our source drain. So that should become a sum of our source drain, good, and also we must have twice times our spacer length. The reason why we have number 2 is both dummy gates contribute the spacers. So that is our consideration. So you now understand that is quite tight. Wow, 34. But we have to introduce certain numbers. So for example, our current value in ASAP7 PDK, this number is number 9 nanometer. Then please try to calculate this LSD length. LSD length just becomes 16 nanometer in this case. It is not that difficult to get this number. So simply speaking, now we have only 16 nanometer long structure, and we must introduce highly doped silicon material on top of this narrow spacing, narrow area. So that is our task. So today, this one will be our second discussion, and first let's discuss about this spacer. So this is usually called as spacer, and we need a low K material. So sometimes we say high K, low K, and please understand this K is originated from Greek letter kappa. So you know this guy, and this kappa is sometimes used as the symbol for relative permittivity. In this course, in many places, I'm just using this epsilon value as for permittivity of a certain material. For example, when I say this epsilon silicon, then it really means permittivity of silicon, and this is corresponding, for example, 11.7 times epsilon 0. So this number, 11.7, the relative permittivity, sometimes just written as epsilon or sometimes written as kappa silicon. So there is no universal agreement on which one is better, epsilon or kappa, but anyway, the name high k or low k comes from this kappa, and they just say k. Well, anyway, maybe you remember that the one of big breakthrough in our technology development was high k metal gate. We introduced high k metal gate into our technology when we found a certain problem from oxide thickness scaling. What was it? So if you remember correctly, if we wanted to have higher and higher C-ox oxide capacitance, then that is given as oxide thickness, oxide permittivity divided by oxide thickness. So in order to achieve this goal, engineers had reduced this oxide thickness continuously, and when it becomes around 1 nanometer, they have found that now oxide is too thin, so our electrons collected by strong electric field can tunnel into our gate directly. So it means that now we have a non-negligible component of gate current. From our assumption, we always think that gate current is almost negligible than drain current, although we have a gate and drain as two active terminals, but gate current is always assumed as close to 0. But that is not the case when we have extremely thin oxide thickness. So instead of that, we have made transition to this one, epsilon of high K material, and also yes, thickness of high K material. If we have a higher epsilon value, then we have a certain margin to keep our thickness quite high. For example, let's say that typical, let me just give you typical value. Epsilon ox is around 3.5, 3.9, and this high K material, usually hafnium oxide or its variant, its kappa value or epsilon value is around 22 or slightly lower. So when we make a comparison, then there is a more than factor of 5 differences between their epsilon values. It means that even though when we increase our thickness by factor of 5, still we have the same electrical capacitance value, while keeping the electrical capacitance same as before, but still we can have physically more than 5 times thicker oxide layer using high K material. And in this case, our tunneling current, our previous showstopper, was quite much suppressed because the physical length is the most deterministic factor to determine our tunneling current. That was the case for our high K material introduction. So we always talk about when it consider this oxide material or gate oxide, we always consider high K. However, in this case, in contrast, we must consider a low K material. It means that we have already given number of 9 nanometer. Here we have 9 nanometer spacing for our spacer, and here we have a gate, and here we have a source and drain. And if we use here high K material, then what will happen? The area capacitance will be just epsilon divided by 9 nanometer. And if we use high K material, then we will have quite a large capacitance. Large capacitance is not a good one between gate and source drain. The capacitance we need to maximize is the capacitance between gate and channel. This one should be maximized. However, the capacitance between gate and source drain should be minimized. So what we are doing is, for example, if we use silicon nitride, having its full composition 3, 4. In this case, usually it has the relative permittivity. This one is a relative one, relative permittivity of 7.5. But then you can ask me this question: silicon dioxide has much lower epsilon values, about 3.9. Then why don't we just use silicon dioxide instead of silicon nitride? However, we have also another problem. Silicon nitride, please remember the name hard mask. When we make a photolithography, we always add hard mask, and that hard mask was made of silicon nitride instead of silicon dioxide. When we make a comparison between these two materials, silicon nitride can be regarded as a much more rigid material. So that is that outstand in terms of its mechanical strength. So it is not that easy to change our silicon nitride into silicon dioxide, which shows relatively quite low permittivity. So what we have done is, instead of completely migrating into silicon dioxide, what we do is, in this composition, add a certain amount of oxygen and or carbon. Then now we have a silicon oxycarbon nitride. So what is the ratio? That really depends on recipe, but depending on recipe, it is known that its value is around 30.8 to 5.0. So I have no idea about what is the real composition, but it is true that if we add more and more these elements into our silicon nitride system, then it is becoming more closer to silicon dioxide, and its permittivity is getting lower and lower. Of course, then you can ask me this question: silicon dioxide was relatively less rigid, so that's the reason why we use silicon nitride as a spacer. Then how about mechanical characteristics of this silicon oxycarbon nitride? Yes, you are right. Compared with this perfect silicon nitride, this one is not very much suitable for spacer purpose, mechanical, in terms of mechanical. So what we do is, in reality, is hybrid low-K spacer scheme means that introduce two different silicon nitride layer whose oxygen or whose carbon components are bearing. So one is used for just mechanical protection, and one is used to reduce capacitance. Now we have this kind of two hybrid spacer scheme. In reality, it is known that they are, I'm not making any device, but engineers are introducing this hybrid low-K spacer scheme. But we will just use one layer named as low-K. So what is it? So maybe mixture of this silicon oxycarbon nitride. And so let's just assume this simple assumption. So please have a look at this one here. This is taken from Global Foundries paper, and now you can see that this is percent of oxygen and carbon. So you can find that some of them is not 100%, or only 50, around 55%, also 55%. It is about only 40%. Well, then what is it? The remaining ones are filled by our nitride. So it means that half of it is fully nitride and half of it, in this case, oxygen. It is quite close to, in this case, silicon ox 0.5 and nitride 1 and nitride 1. This is the composition, and if we increase carbon a little bit, then kappa is increased, and if we reduce the sum of nitrogen and oxygen simultaneously and increase nitrogen composition, then of course we are approaching higher kappa value. It is quite acceptable. If we increase the nitrogen composition further and further, then our material will become more rigid and showing higher kappa value. So we must have a certain compromise, and this hybrid scheme is a good way to get both benefits: reducing capacitance using most of this layer is made of relatively low kappa material, and the how can I say, the outer shell of this material is covered by more rigid component. That is the one we have. Anyway, we are sacrificing our 34 nanometer by amount of 18 nanometer for our spacer. So please now do your own exercise. That was our previous structure. Now we have 3 dummy gates, and later this part will become M MOSFET and this part will become P MOSFET, whatever. And now we have a hard mask. Maybe this hard mask thickness is slightly overestimated, so it's, well, when I made it, so I saw wrong number, so it is a little bit too tall. But anyway, now we have this shape, and please deposit our silicon oxycarbon nitride layer isotropically. So what should be the thickness? Yes, we must introduce 9 nanometer, because the final thickness of our spacer we wanted to have is 9. Therefore, deposition should be also be done with 9 nanometer. You know this one quite well. So let's say that now we have a certain structure, and if we add 9 nanometer, then we will have just 9 nanometer from this point position, and from side wall we still have a 9 nanometer and 9 nanometer and also 9 nanometer, and we will have quite conformal shape of our deposited silicon oxynitride. And you know that the next step, next procedure is just to etch this oxynitride with anisotropic etching process. So just to etch from G directional concentration. So if we just eliminate 9 nanometer, then this part will be completely gone. The point is here in this tall structure, due to its anisotropic nature, we will have just only slightly reduced values for our spacer. We have already seen it when we talk about self-aligned quadratic patterning or double patterning. So that is the sidewall formation. Yes. And what is the size of this lateral size of this remaining sidewall? Of course, this is corresponding to 9 nanometer, because we made isotropic deposition, so we have grown along this vertical direction 9 nanometer, and it is still there. So if we wanted to have 9 nanometer thick spacer, then we have to do this 9 nanometer thick isotropic deposition. Of course, my discussion up to now is assuming perfectly isotropic deposition and perfectly anisotropic etching. Is it really true or not? Of course, we must consider a small margin for this anisotropy. So maybe the sidewall can be slightly etched away. So if we really make a 9 nanometer, then remaining one can be slightly thinner than 9 nanometer. Then what is the reality? Our engineers, the unit engineers for this etching process, they do repeated job for these patterns and check that in this process condition we can safely have 9 nanometer as a final one. So whether we make the exact 9 nanometer at the beginning, that doesn't matter. Important point is the final product, final shape should have 9 nanometer. So that is done by repeated experiments. So please understand, this is just a rough sketch and the actual condition should be calibrated. And now we are using 9 nanometer, but if this is instead of 9 nanometer 10, we can think about 11, 12, whatever, up to 17 nanometer. Please think about the extreme case. We have introduced 17 nanometer thick spacer. What happens? Okay, we have a quite good electrical separation between source and gate, and drain and gate, but there is no room for our source and drain. Our 34 nanometer is completely just filled by our source and drain spacers, and there is nothing for silicon source and drain. In that case, we can think that narrow source drain window is left, and it is directly affecting quite large source drain resistance. That is quite bad. Okay, then let's go to the other way around. Instead of this 9 nanometer, why don't you just make it thinner and thinner? And if we go to, for example, 1 nanometer, wow, if we go to 1 nanometer, then we have 32 nanometer reserved for silicon source and drain. So we can put a lot of silicons into it. So resistance will be quite small. So that is quite good. But at the same time, the capacitance, here capacitance means that capacitance between gate and source and gate drain will increase quite rapidly. So maybe you can think about this one. Well, anyway, more important one is resistance. So let's just make this selection, but that is a wrong assumption. So nowadays important one is called as performance, and this performance is not our own current itself, but performance is measured as just frequency of our operation. How much we can increase our operation frequency. So if we reduce the resistance, then of course we can increase our own current. However, at the same time, if capacitance is increased, then this increased own current is used just to fill or charge and discharge this increased capacitance. So this is not a good way to make a better performance. So then is it this one is the right direction? I don't know, because reducing capacitance also good, but there is also trade-off of increasing resistance. So in reality, the optimal point does exist in between. We must do some optimization by changing this spacer. Then later we can have certain acceptable value of capacitance and acceptable value of source drain resistance, and their combination give us best performance in terms of performance or in terms of maximum operation frequency. That requires the real optimization. Okay, so anyway, I will just, so then next question, have you already optimized this example with 9 nanometer, 8 nanometer, 10 nanometer? No, I haven't. Just I'm showing the value given from our ASP7 specification. Later, I guess that maybe it can be a good topic for your term project. Later, you will do your own term project, and maybe one of the research item or term project theme can be changing this thickness and observe the change of your resistance and capacitance and eventual change in your operational frequency. That can be a good way to do your term project. Okay, so this one just showing the things I have already covered. Now we perform anisotropic etching of this spacer region. Then now we have this shape. I wanted to say one thing more. So previously we had the spacer covered here, and they are gone and they are etched away. But this is okay, but please have a look at another point here. Now you can see that here we have exposed source and drain region. This part should be later filled with additional source drain silicon, and that is, previously it was also covered by this part is also covered by spacer, because this spacer deposition was done globally without any patterning for our source and drain. And also here you can see that here we have previously we had fin, and even this fin, it generates a certain sidewall spacer. Okay, compared with this dummy gate spacer, it is relatively shorter, but still we have a fin and it has a certain amount of spacer. So if we just make just 9 nanometer etching, then what will happen? then we can completely eliminate this guy, good, and also we can eliminate this guy, good, and also the one here can be eliminated. However, the one in fin, what will happen? The top part will be etched away, but still we have a relatively short fin side wall, and this fin side wall should be, well, this point is, I'm not that much, well, I have to admit that I'm not that certain. And even when we dig out the literatures, sometimes depending on companies, certain companies just left this side wall to guide our later process, or sometimes they completely etch away this side wall. Frankly speaking, I wanted to make a conclusive answer for this issue and try my best to find out the one way, but well, unfortunately I failed. And it seems like that nowadays this fin side wall is not remained, so we etched away in this style. So now source drain region is completely etched away. Now this side wall is etched away, and our silicon is just exposed to. This is not exactly silicon, but silicon dioxide, but dummy dielectric is exposed in this example. But well, this point is not that certain. Okay, so I think that this is a typo, covering the dummy gates. Okay, so therefore your etch depth should not be just exactly 9 nanometer. In order to get this kind of a complete exposure of our fin, then we need a slightly thicker etch depth. So one of my recommendation is, please try to find it by your own experiment. If you do it just 9, then you will have a remaining side wall here. Okay, so now we assume that we make a complete etch away of our fin side wall. So the next step is now our second topic, source and drain epitaxy. So now we have made channel called as fins, and we have made a dummy gate. Later we will make another real gate, but right now that is just a polysilicon, and we have introduced low K spacer to separate them. That means that gate and source drain. Then now it's time to do this source drain epitaxy. So this is a top view of our current situation, and this purple one is, now you understand, this is corresponding to our silicon oxycarbon nitride, and this is a dummy gate, and this is the place for source and drain epitaxy. And this this one, this here we have just a lead region, and in my current example, this lead region is corresponding to silicon. Then just doing silicon oxynitride etching, so still we have a dummy gate. This green one is this green one is a dummy dielectric, so corresponding to silicon dioxide. So in order to make another exposure, then we have to remove this oxide without any patterning. In this case, because this one is silicon nitride, and this is also silicon oxynitride, so we can have a sufficient selectivity between this one and silicon dioxide, and just to remove oxide. Then we will have just to expose silicon fins. These are really fins, and this part is covered with steel dummy gate, and below STI. Dummy gates are silicon dioxide, STI, they are also silicon dioxide. So we will have this top view. Maybe you can ask me this question. Up to now, our code, Armstrong-Craft, always allows anisotropic etching. So always G-directional etching was allowed, but in this relatively new release, now you can just specify ISO option, then you can do isotropic etching. So where can you find it? Here, etch, parenthesis, and now you have ISO. If you do it without ISO option, then you will find that still you have a sidewall corresponding to the dummy gate. But if you activate this ISO option, then you can find that it is well eliminated from your final structure. Why it is important to remove this oxide? Because from now on we will do some technique called as selective epitaxial growth. It means that from the top view you can find many different materials like silicon dioxide, silicon oxynitride, and silicon nitride, and pure silicon. We have a certain technique, fabrication technique, to grow silicon only on top of silicon. So it is not like so I think that it is not a good analogy, but let's just make my own analogy. So previously, when I talk about deposition, I made some snowing example. So we had a ground, and snowflakes come, and after that we will have a certain layer of snow. That was my own example or analogy for snowing. I'm not saying that this is completely correct, but now let's think about this one. Now let's make a pattern of our ground. Our ground previously was just made with soil only, but now instead of this soil only, let's make a good metal plate, and also make a good metal plate. And once again it snows, then snowflakes comes. However, when this snowflake just attached to metal, then what will happen? In this case, metal has quite a good thermal conductivity, so it is just completely melt out, and there is no snow accumulated on top of this metal. However, soil has a relatively low thermal conductivity, and after that you can find that there is a certain layer of snow, but for good metal there is nothing. Maybe you can see it quite well when you go to certain parking lot, for example, on top of ground. So although there is a certain amount of snow, but usually for your car, on your car, you don't have the snow layer, and instead on glass layer, so the front glass layer, you have a certain thickness of snow layer. So quite similarly, I'm not saying that this is perfectly analogy, but if we have already patterned wafer, then although we just put our element for deposition without any further consideration, but that grows only for place we have sufficiently good conditions. That is the selective epitaxial growth. Especially we will use this technique for silicon growth on top of silicon. So only when we have silicon is grown. On top of silicon nitride, silicon dioxide, they don't grow. Then why it is good? Because if we have such a selectivity due to its own process, we don't have to any further patterning. We can reduce several photolithography steps that is directly related with two things. One is we can reduce the number of masks related to this process. That is critically related to manufacturing cost. Another one is due to its own selectivity, we can even further miniaturize this source drain region. So that is always good. So selective epigrowth technique is used, and we will talk about this one. Yes, and this is our consideration in Armstrong craft, and this one is a TM image from certain company, so which make investigation on already fabricated product. There are certain companies like this. They bought the lawful product, so already in market, and they make certain wafer cut and digging out what is inside it and make analysis and share the information to their customers. That is, I took this information from internet, and this is our expectation what happening in our process step, and this TM image taken from Samsung's 14 nanometer FinFET source and drain. Where are we looking at right now? Well, although this is a three-dimensional structure, this is just showing two-dimensional cross-section. Then where is the cut plane is placed, and this cut plane can be found this point. We made a cut over this source drain region, then you can find this one. So simply speaking, here we have 4 fins, and these 4 fins, of course in our case 3 fins, then we can identify here, and another 4 pins for P MOSFET we can find there. That is our 2 islands for N MOSFET and P MOSFETs, and you know that here we have a certain empty places. Of course, fins were formulated quite uniformly. So previously there were also fin. I'm not quite sure there was 1 fin or 2 fin. Maybe here they had 1 fin and they had another fin, but they are eliminated in this case. So we did it also. You can see the one shown here. We made a fin cut. So this one is corresponding to fin cut, and we don't consider this even deeper one. We just made a simplification. And most important one is, okay, now up to now you can understand we have fins, and we have fins, and we have fins. They are fins, but when you have a look at this line or this level, then you can see that there are diamonds here. There are diamonds in P MOSFET, and in this M MOSFET, the shape of a diamond is not as beautiful as P MOSFET, but they have a certain, well, sometimes they call it as a mushroom shape, but anyway, there is also similar thing. Means that now we did something for this point, something to fill this empty space with silicon, additional silicon, and this is corresponding to added silicon. Of course, silicon or silicon germanium, but right now just to consider silicon, and we have added additional part. Our original fin was just looks like just fin, but we introduce something on it. So this new part is added to have the real source and drain. This is the important step for source drain epitaxial growth, and we adopt selective epitaxial growth. So we do not do any further patterning, just try to grow silicon on top of silicon, not on other materials. That is the key. And so from now on I will talk about then how can you actually do it, but it will take some multiple lecture slots. But before talking about this one, I wanted to mention this issue, merged source drain. So you know that there are 1, 2, 3, 4 pins, and also 1, 2, 3, 4 pins. They are, of course, later will be covered by the same gate material. So, for example, you know, this one, this is a dummy gate, and this dummy gate just covers all over our 3 MOSFET part and 3 PMOSFET part. Yes, they are controlled by the same gate voltage. But here, we are now currently looking at not gated part. This is not gated part, but just source and drain. And they are, different fins are merged. So even in this silicon level, they are merged. Then is it good or bad? Please think about the pros and cons of this merged source and drain. If we have this merged source and drain, then of course we have a wider silicon, so good for reducing the resistance. Good. But another point is, if we do this kind of a relatively large source and drain, then it is really difficult to control variation. Sometimes they are merged, and sometimes they are not merged due to process variation. Then what will happen? Merged one will show lower resistance, and unmerged one will show relatively higher resistance. So always lower resistance is good, but also we have to consider variability. If you make a billion transistors, good one is good, but bad one is too bad, then that kills your design. That is not the way we prepare. So, well, also I have dig out many papers, and generally speaking, people wanted to have unmerged, separated structure. That is my current understanding. But depending on the TM image, sometimes they really show merged one and unmerged one, and their real advantages or disadvantages is not that much clear. We cannot definitely say that we always avoid this merged one. So maybe you may remember in our previous ASAP 7 ASAP 7, yes. So this is the assumed structure of our source and drain, and here we have 3 fins, and even in this ASAP cross section they assume that here we have diamond structures and these diamonds are merged together. I think that because at that time that was technological standard of what TEM is taken from literature, so that's the reason why they make this merged assumption. But I'm not that sure about that. So another one I have seen from the literature is like this. Maybe let's just make a certain rough estimation. So right now we have a 7 nanometer thick fin and 7 nanometer thick fin, and in between we have 20 nanometer. This 20 nanometer is about 3 times of our fin thickness. And when I have a look at the top view from this wafer surface, usually what we have is if we have to grow source and drain here, then here we have the grown source drain epi and also grown source drain epi. So simply speaking, if this is 7 and this wing is around the fin thickness, and also this wing is also around similar number, so this spacing is more or less divided by number 3, and here we have sufficient room to separate them. That is seems to be usual way to do that, but I cannot say definitely because the number of available TF images are so small, especially many literatures just to show this beautiful graph. This single fin shape, beautiful diamond is always shown in many literature, but in reality, single fin does not exist. Did not exist previously. Of course, in the latest fin technology, we allow, or TSMC allow, single fin transistor, but usually we have multiple fins. And what is their relation between two fins? Are they merged or not? Is not disclosed quite clearly by many papers. So please understand certain uncertainty because we are already quite close to mass production. So I have no definite information about the real one right now. But anyway, that was about merged source and drain. So in this work, I will try to make an unmerged one because that is known to be more safer in terms of manufacturability. For example, if we make it just merged one, then what will happen to this guy? Underneath of these two merged one, how can he feel something into it? So now let's go to our second topic, selective epitaxial growth. I have already explained the main point. In this procedure, we wanted to grow silicon only on top of silicon and not on top of silicon dioxide and silicon nitride. So actually this technique, selective epitaxial growth, was initiated several decades ago. So this paper, if I remember correctly, maybe this is around about late 90, but even at that time, the selective epi growth was not the new technique. It was known to us, however, was not applied to the actual fabrication. The point is, now we introduce this kind of thing. First of all, we use reduced pressure chemical vapor deposition. What is it? I have a little idea about that. But reduced pressure means that its pressure is much lower than air pressure. In that case, we have a certain chamber, and instead of heating the entire chamber, we have only one place for one vapor, and this vapor is locally heated. The reason why we do local heating for this system is, if we heat the heat up the entire space, then this reaction, silicon deposition, can happen everywhere. We wanted to minimize this unselective silicon growth, so we wanted to grow silicon only on top of a vapor, so we just heat it locally here. And pressure is low, and we introduce a gas called as a DCS, dichlorosilane. And silane, actually it has the chemical formula like so silicon H4. So this is a gas, and there is one silicon atom, and it has 4 valence electrons, and they are connected to surrounding 4 hydrogen atoms. This is silane, original silane, and this silane is known to be quite much proactive for chemical reaction. However, in this case, instead of this silane, we introduce dichlorosilane. It means that 2 of hydrogen is now become just a chlorine atom. So this is the one. The reason why we are using this DCS instead of silane is it has lower activity. So it is not as active as silane, because if we use silane, then this process becomes too active, so we cannot control it. We have to reduce the reaction speed. That's the reason why we use this DSC. And this hydrogen is just used for carrier gas. This does not do anything, just to flow our other gases and make a certain flow of because here we have a chamber and gas in and gas out. In order to make this inflow and outflow, we must have another gas. So that is just a carrier gas shown here. So using this one, and with a certain heat, elevated temperature, like depending on the situation, about in Celsius, it is around 550, 600, 650. These are the numbers or temperatures used for this reaction. In that case, quite naturally, this guy, DCS, is decomposed into these 2 parts, silicon, solid silicon, so it is attached and nuclearized. And also we have hydrogen chloride gas. This is still gas. That reaction, this directional reaction occurs. That's the reason why we have growth of silicon. The natural question is, okay, if that happens, why do we have selectivity? Why this reaction happens only on silicon and not on silicon nitride, not on silicon dioxide? Actually, it really happens. So in the case of a silicon oxide. So I'm not quite sure you can see it clearly. So let me just draw it. Here, let me just draw it. Here we have a certain layer. This layer is corresponding to silicon nitride. And originally we had silicon layer beneath of it. And here this part is covered by silicon nitride, and this part was just exposed to the air. Then what happens? The original silicon layer, on top of this original silicon layer, we have a certain growth of epitaxial grown silicon. This is what we wanted to have. However, when you have look at the point on top of silicon nitride, even on top of silicon nitride, you can find something. What are they? They are also silicon. These silicon nucleation can be observed especially on silicon nitride. On the same paper, they did also the same patterning for silicon dioxide, and on top of silicon dioxide we don't have any of this nucleation. So it is very difficult to formulate this silicon chunk on top of silicon dioxide, but it is easy to make it on top of silicon nitride. So what they did, they really wanted to have selectivity, so add another one, HCl. So HCl is added on etching gas. Then the real key is in this part on top of silicon, the reaction is quite fast. Nucleation is quite fast, and silicon nitride, it happens but slower than silicon case. By using HCl, this small generated silicon nucleation, they are continuously eliminated, and we have a quite beautiful clean surface even when we have silicon nitride. It means that we have to control the amount of this DCA gas and HCl gas and temperature and time quite tightly. So otherwise our output will not as clean as we want. So we have to optimize it. But roughly speaking, this is the way we have selectivity. So if on top of silicon the growth rate is best, so we just remain or keep that one only. For other ones are just suppressed by this etching gas addition. So that is we wanted to have. But here we have some unwanted phenomena called as facet. So face, sit. So this is face of a certain crystal. So this is the facet is observed here. Please make a comparison. They made also same pattern using silicon dioxide and silicon nitride and try to grow silicon. So if this is perfect, then we can just expect that within that window, open, this is open, and this is open, and this is not open by or masked by silicon nitride. So we just expect just a uniform growth of silicon layer, epi layer, and now we have quite good epi growth for silicon nitride. But unfortunately, if we go to silicon dioxide mask, then what happens? You can clearly see that here we have certain behavior. and also you have certain behavior and certain behavior. It means that when your silicon is just attached to silicon dioxide, that part is not growing as fast as this bulk point. If we, so you know, this is the situation. Here we have a silicon dioxide, and here we have just a bulk point. The point is shown here and shown here have different growth rate. This one grows fast and this one grows slower. That's the reason why we have this kind of unwanted facet. Then you can ask me this question once again: why we have a different behavior between silicon dioxide and silicon nitride? Please come back to our previous one. You know, this nucleation happens only on silicon nitride. It means that the growth rate was quite fast for silicon and much lower than silicon nitride, and almost zero for silicon dioxide. So in this case, silicon nitride, although not as fast as silicon, but it is just okay to support the uniform growth. However, in the case of silicon dioxide, now on just nearby silicon dioxide, it cannot grow quite fast. So that's the reason why we have this well-known facet occurrence. Well, then let's live with it. Yes, currently means that in FinFET technology, we live with this facet formation. So we don't care about it. But point was, previously, when it was first introduced, our technology was just planar MOSFET, and what they wanted to do was, yes, here we have a source drain, here we have a source drain region, and we wanted to make selective epigrowth on top of this source and drain region. And depending on this facet case, sometimes we have a certain behavior like this. This is grown episilicon. Doesn't matter. At the time, it was a serious problem because here we have a thickness difference. So engineers were worried about maybe this one is almost uncontrollable. So therefore, the thickness makes some differences, and especially in this part, actually we have no epi at all, and this part will increase the leakage current. That was their concern. So they did not use this selective epigrowth technique for a long time, although that has been known to us quite a long time. However, in FinFET case, we adopted this silicon epigrowth. Also, even I'm not saying that in planar case we have not used selective epigrowth. No, late 90 they did not use this selective epigrowth, and later they adopt in planar MOSFET fabrication. And I guess that this is the final slide of today's lecture. Then why we have this kind of a facet? So I already told you that some part it grows fast and some part it grows slower. But what is the mechanism for behind it? And now these two TEM images are taken from the same sample, so same lot, and they just make the growth of 60 nanometer thick epi layer, and they made 4 times thick epi layer growth, 60 nanometer or 240 nanometer. at the beginning of this initial phase, what you can see clearly is this slope. And later, if time elapses, then you cannot find this relatively low angle slope any further, but you can see the one much, how can I say, much steeper and also moderately steeper. So means that starting from this relatively moderate angle, if we go to even thicker case, then it becomes steeper and steeper. And if time elapses further and further, what remains is eventually this one remains. Its angle is more than 50 degree, and this one will be the typical behavior of our long-term selective selective epitaxial growth. Then why do we have this kind of quite characteristic surfaces for these silicon growth? That is directly related with the final shape of our FinFET source and drain. Actually, you can have this diamond structure, and this diamond structures, this angle, actually this angle is corresponding to the one you are looking at the end of our presentation material. This guy. This guy, the 111 facet, is the one why we have diamond. So we have 111, 111, and 111, and another 111. So and of course this angle is higher than 50, so they are not exactly 90 degree. They have a certain angle larger than 100 degree. And now we have this final bottom line is of course given from its silicon fin structure. So that's the reason why we have a typical diamond structure. Then why do we have this diamond structure, and what is the magic behind it? It is critically important for FinFET because the source drain resistance is solely given by, or largely given by, the shape of our diamond structure. If diamond has large, then of course we have a lower resistance, and this volume is small, then it has also increased resistance. So that is a topic of much research, but well organized and summarized review on this one is still missing, at least to me. So in next lecture, I will try to deliver my understanding as much as possible. And final comment is, unfortunately, our current implementation of this Ångström craft cannot really generate this diamond structure, because later we will see this diamond structure is obtained from anisotropy of growth, at the same time also related with the boundary condition. So it is a quite complicated one, which is far beyond than the current capability of Ångström craft. So we will just make a crude approximation for the real shape. So please understand the limitation of our process emulation. Okay, so let me just finish today's talk with homework announcement. It is quite same as before, just to follow our process emulation result. But the second part, the epigrowth, is there is nothing for you to do right now. You will just free to just study the contents, and please do your process emulation only for spacer generation.